Hello everyone and welcome to Team 19104's Virtual Design Day presentation. Over the next 8 or so minutes, we will be highlighting our process in creating the smart ultrasound marker, also referred to as the SUM for brevity, that we were tasked with creating by our sponsors at Becton Dickinson Peripheral Intervention.
Today, we are going to highlight the major aspects of the engineering design process that we have focused on this past academic year. We're going to conclude with the lessons we've learned and challenges we've overcome along the way.
Before we begin, we wanted to give a quick introduction of the team members, reading from left to right. On the far left, we have Andrew Clark, who is our mechanical engineer. And then Hannah Gerson, Brandon Wynn, Jacqueline Niesman, and Ryan McNamara are all biomedical engineers. And on the far right, we have Noah Thurston, who is the team's electrical and computer engineer.
We will now provide a brief introduction for our project. The current gold standard for tissue biopsy is conducted using stereotactic imaging, which involves X-ray radiation and prolonged immobilization of the patient. This can often be more expensive and uncomfortable. An alternative approach is presented by ultrasound technology, where the biopsy needle is visualized using an ultrasound unit that has no radiation and allows for improved comfort. The main problem with ultrasound-guided biopsy is the lack of relevant spatial markers on needles and lower resolution. This lack of spatial awareness can lead to improper sampling of tissue and false diagnoses. Our project aims to improve spatial information by leveraging material properties and computer vision to reduce the risk of incorrect sampling. Our approach to the problem was to create a low-profile marker that would attach easily to existing biopsy needles. This marker possesses unique sequences that are created using 3D printing. Existing ultrasound technology has the ability to distinguish the pattern of these unique sequences, and based on images that are captured using the ultrasound unit, our novel identification algorithm can generate relevant spatial information about the needle position and orientation within a tissue. This diagram provides a more detailed view of how the entire system is assembled and how the mechanical aspect shown in the red square interfaces with the software aspect shown in the blue square.
We're now going to go into the project requirements laid out to us by our sponsor, BDPI. Here we have the 7 overall requirements for our project. The SUM shall be distinguishable and locatable under ultrasound in frontal, sagittal, and axial planes. The SUM shall be compatible with a 7G needle provided to us by BDPI. The SUM shall not increase the profile of this needle by more than 1 gauge size. The SUM should be biocompatible. The SUM shall have a software that will accurately auto-recognize features with a user-friendly latency of less than 30 seconds. The SUM shall have software that will interface with existing ultrasound equipment, and the development cost of the SUM shall not exceed $4,000. In terms of accuracy, the SUM shall be locatable within 1 centimeter of the real physical distance and shall be visible and clear at a depth of 6 centimeters, both with the naked eye and with the computer program. The SUM shall be compatible with the 7G needle, which has a diameter of 5.156 millimeters, and the SUM shall be secure on the needle, not moving by more than 0.1 millimeters during biopsy. The SUM is also required to not increase the gauge size of the needle by more than 1. For a 7-gauge needle, this would mean not increasing the diameter by more than 0.45 millimeters. A large part of biocompatibility involves safety, meaning that the materials the SUM is made of shall be safe to use within the human body. In order to confirm this, we chose a material from the list of FDA-approved materials, and we confirm that it is safe through their website. In order to be biocompatible, the SUM also needs to have an operational temperature between 36.1 and 37.2 degrees Celsius, meaning it shall not degrade within these temperature ranges, and this is the standard temperature range of the human body. In terms of our SMART program, the software should auto-recognize the unique sequence on the SUM with a latency or delay of less than 30 seconds. The SMART program should have a GUI that relays the position of the SUM and the needle tip to the user in real time, and the software shall auto-recognize the features of the SUM with an accuracy of at least 90%. The SUM software shall also interface with existing ultrasound equipment, meaning the computer will communicate with the ultrasound to receive information through a digital or analog interface. And lastly, the total cost of developing the SUM shall not exceed $4,000, which does not include the materials received from BDPI.
We will now look at the trade studies portion of our project. Out of 3 competitive designs of unique material combination with different materials, unique geometry with different geometric shapes on each side, and unique sequence that involves slits, our team ran a pros and cons list and decided that the unique sequence design was the best for this project. As you can see below, there are now 4 equally spaced unique designs on each side of the sheath. The purpose of this is to allow more spatial awareness of the sampling notch in multiple planes. This slide shows the hypoechoic material our team used during the project. Using third-party vendors and the AME machine shop to 3D print, our main concern was biocompatible material. Our team chose to use Somos 9120 as a material because we discovered that not only is it biocompatible, but it is widely used for medical devices. Both materials shown are echogenic. Tissue mediums are used to mimic human tissue. Since our project involved medical situation testing, the next best thing of our human tissue was to use tissue mediums. Our main use of tissue mediums were beef and chicken. Ballistic gel was used towards the end of our project to allow us to clearly see exactly where the needle was with the naked eye.
Now I'm going to discuss the verification and validation of our prototype. Here we see the results of our tests. Under the material detachment category, we see almost no rotational or lateral movement. Under visualization, we see we were successfully able to detect the marker up to 6 centimeters deep. Now, we weren't able to reach our goal of 90% accuracy in the sample notch detection, but this specifically tests for our ability to predict what orientation we were in. And when it came to just predicting what position we were in, we were able to predict it with 100% accuracy, as well as predict in all 4 of the goal planes. Here we see our deliverables to the sponsor. This includes this drawing set, the SolidWorks model, the Smart Program GUI software design document, the Smart Program written as a Python script, and then finally the test procedure and the test report.
Up until the COVID-19 pandemic, team meetings and testing was performed in various rooms that we rented out in the Science and Engineering Library. The image on the left shows the ultrasound, biopsy needle, and the various tissue mediums that we tested first semester, including raw chicken breast, raw beef, and ballistics gel. We made sure to wear gloves and use antiseptic wipes upon completion of testing. The image on the right is a demonstration of the wired interface that allowed us to directly stream the ultrasound images to the laptop and software in real time. To accomplish this, we used an analog to digital converter along with the USB capture device. These 4 images are what each side of a marker looks like under ultrasound. We see that the marker makes each side distinguishable to the human eye, and this was verified in a test with a trained ultrasound technician. This proves that the marker is able to enhance the spatial awareness of the sample notch on the needle.
Now I'm going to give a quick demonstration of the SumSmart program. First, we're going to load an image. Select this one right here, and now click Execute. Now, what's happening right now is the Sum program is attempting to do 2 things. 1, predict the trajectory of the needle, and 2, look underneath that trajectory for any shadows cast by the smart markers. Using those markers, it'll attempt to predict the orientation. Here we see the predicted orientation as front sagittal, as well as the identified markers that it used to predict the orientation. Lastly, we see the latency marked at the bottom for the user.
Over the course of our project, we encountered many design-changing obstacles. This taught us how to be adaptable at all stages of the engineering process. And in regards to the research that needed to be done, we learned that getting individual insight from a specialist is very helpful, and this should be done at earlier stages of development. This would have possibly solved many of the problems that we faced during prototyping. We would like to acknowledge our team sponsors, Summer Garland and Genevieve Messina at Becton Dickinson, Emily Caleo, an ultrasound technician at Southwest Advanced Vascular Surgery, and Don McDonald, our team mentor, for guiding us through every step of our project.